Yeah, let's. So let's go back to our symplectic geometry and moment maps, and I wanted to spend maybe 5 or 10 more minutes talking about convexity. So let me recall that we proved the main part of the convexity theorem over the last 2 classes. So let me state it again. So we have C acting on M omega mu, a compact connected Hamiltonian T-space. And then there are 2 things. First of all, the image of M inside T star is a convex polytope. And this statement we actually proved. But then there was a second statement saying that mu of M is a convex hull of the image of the fixed point set. So let's discuss this statement. Right. So perhaps it's a combination of 2 small remarks. So one remark which is obvious, mu of M is a convex hull of its own conus, right? So we know that mu of M is a convex polytope, and then a polytope, it's a convex hull of its conus, so it's the set of convex combinations of the corner points. Right, so now let's go back to those local normal forms of mu. So if we have a point M in M, and we consider some open neighborhood of this point, then we know that the image of this open neighborhood can be represented as an intersection of some polyhedral cone shifted by mu of M, intersection with some open neighborhood of mu of M, right? So that's how it looks like. So let me recall in a bit more detail. So we have here mu of M, and so there are some flat directions, and there are some polyhedral directions. So that's this polyhedral cone which is shifted to mu of M, and it's intersected with some open neighborhood W, and their intersection, that's the image of the of a neighborhood of M. So that's the picture that we were basically exploiting all the time at the last lecture. Now the question is when mu of M can be a corner, right? So mu of M being a corner, this means that the local picture should be like that. So it should be a polyhedral cone, but no flat directions, right? So let's recall when we were developing the local normal forms, first we obtained such local normal forms. And this was for the points of the fixed point set. And then we worked out more general local normal forms, and that's where the flag directions appeared, right? So, so the statement is, so if the local normal form is like that, so then this means, so that's mu of m. So this means that m is in MT. So let me recall that the formula in local coordinates z1, zs, it looks like mu of m plus 1/2 sum of zi squared. And here there are some weight vectors. Now maybe one important remark or one test question. So, so for the picture to look like that, you need M to be in MT. But is it true the other way around? Suppose that M is a fixed point. Would mu of M be necessarily a corner? You see that's the formula, right? So that's the local normal form for a fixed point. So let me just give you an example in dimension 2, how it may look like. So suppose, so that's our mu of m, and of course the image will depend on those weight vectors, right? So imagine the weight vectors they look like that, for instance. Recall that here you may need a lot of those weight vectors, right? So the number of weight vectors, that's half of the dimension of our manifold. So here we're doing something for an 8-dimensional manifold. So what would be the cone in this case? Right? So these are the weight vectors. We're spanning something with those weight vectors times non-negative numbers, right? So this means that mu of m plus Cm will be a polyhedral cone of this type, and clearly this point is a corner of our future polytope. Right? But it may also be like that. Right? So this might be our weight vectors. So what do we get in this case? So what's the image? Everything, yeah. So those combinations of weights, they will just give you everything. So this means that this point is clearly not a corner. So in fact, to be a corner, you need to be a fixed point, because otherwise there will be those flat directions. But not the other way around. If you're a fixed point, it may very well be a point somewhere in the middle of the polytope. So there is no problem here. All right, so what those local normal forms are telling us, they're telling us that corners of mu of m are contained in mu of ft. And this, of course, means that corners hull of corners is contained in the convex hull of mu of mt. But we actually know that, well, of course, mu of m, since it's a convex polytope, it's a convex hull of conus. So it is contained in a convex hull of mu of mt, which is, of course, contained if in mu of m simply by convexity. So, so this finally means that the convex hull of conus is mu of m, and the convex hull of mu of mt is also mu of m. So here actually we have an equality, and here we have an equality. Right. Okay, so this finally finishes the proof of this convexity theorem. Perhaps, well, one important remark, which actually would make a smooth transition to the next topic. So suppose that, let's denote the dimension of m by 2n. And let me recall that we have the Liouville volume form. Volume form on M. In fact, one can think that this volume form, perhaps it's just a matter of terminology. We can think that this volume form defines a measure on M. So it defines a measure on M. And since M is compact, volume M omega equal to the integral over M of L is finite and positive. So it's a positive real number. In principle, we can normalize this measure to be a probability measure if we divide by this volume. Now, well, we have a map to the image of M inside T star. So this is a convex polytope. And now we can kind of, for measures, the natural thing is to consider push forwards, right? So let's consider the push forward of the Liouville measure on M to mu of M. So mu star of L. Push forward. Measure on T star, we can say supported on mu of M. So we make a push forward and we get a measure on this vector space T star, but of course it's only supported on the polytope, which is the image of our manifold. So this measure is called Duistermaat-Heckman measure of M. So the notation is, well, one of the notations is DHM. And so that's the measure on the polytope. So you see, this introduces the whole new dimension in our discussion. So we have a manifold. We associate to it its moment polytope, which is a combinatorial object. But it turns out that this polytope is actually equipped with this measure, right? So let's discuss a little bit the properties. Let's discuss the properties of this measure. In fact, since our time is perhaps a little bit short, I decided to do at least the main part of the discussion for the case of the circle. So remember, we started in the beginning of the course with an arbitrary action of a compact connected Lie group, but then many things we did for tori, but now let's further simplify things and let's discuss it for the group being just S1. And let me try to state a theorem. So we have S1 acting on M omega mu. Mu is now a map from M to T star, which is just isomorphic to R. So mu becomes just one function. So in compact connected Hamiltonian S1 space. So let's choose a point x0 in mu of M. A regular value of mu. And to simplify things, let's assume that the S1 action on the level set is free. So, then there will be three statements. First of all, for x in some open neighborhood of x0, the reduced spaces will be diffeomorphic to the reduced space at x0. So this is second, so the volume function on the same interval, the volume function is polynomial in X of degree bounded by n minus 1. So n was half of the dimension of the manifold. And finally, again, on the same interval, the Duistermaat-Heckman measure of M. So now it's a measure on the image of M. The image of M is a convex polytope in R, which means a closed segment. Right? So it's equal to 2 pi times this polynomial volume function times the Lebesgue measure dx on the real axis. So that's again for the restriction of the measure to this interval. Right. So maybe here let me draw a picture. So here is our manifold. So that's the real axis, and that's the moment map. So the image of the moment map is this interval. So we choose a regular value. A regular value, so means that here the fiber, the pre-image, is a submanifold. And we're saying that somewhere around this regular value, one can always find an interval such that the situation is really very, very nice, right? So all the reduced spaces, they are diffeomorphic, so the reduced space doesn't change as a manifold if you move around that point, right? So the volumes of them do change, though. So they change as polynomials. And moreover, we can read it. So they're kind of intimately linked in a very direct way. So if you just take the push forward of the measure, this measure is more or less this volume function. Right? So this means that whatever way we want to turn it, typically we think that the information about the big manifold is easy, and what is difficult is to find out something about the reduced spaces. So we can mainly think of it as a way to compute, for instance, volumes of reduced spaces. Okay. Now that's how it looks like. Well, let's try to prove this theorem. But before doing that, I need a small piece of technique, which probably you know. So I'll spend maybe 10 minutes speaking of connections and curvature on principal S1 bundles. It's probably something that you heard of, right? Everybody? Do we need to? Oh, okay. No, but okay. Let's do it. 10 minutes catch up. So. So let's say we have an S1 principal bundle. Recall that basically in our context this just means that we have a free action of S1 on P. So then there is a nice quotient space, and actually using our normal forms theorem around the orbits, we know that it's locally trivial. So it's covered by charts, and over charts P is simply isomorphic to U alpha times S1. So let's denote by V the fundamental vector field of the S1 action. Now, definition. One form on the total space is a connection. One form if it satisfies two properties. Theta is S1 invariant. And it's pairing with the fundamental vector field is simply equal to 1. So let me briefly say Why such forms exist? So locally, I recall our bundle, it looks like just a product of some chart times S1. So we have U alpha cross S1, and we can say that points here, or coordinates here are some x1, xk, and here the coordinate, let me call it phi alpha. Now the fundamental vector field in this chart, it of course looks like a rotation around S1. So we can locally choose the one form theta alpha just to be the differential of phi alpha. Obviously, it satisfies both conditions. It's invariant under shifts, under translations with respect to phi, and it clearly satisfies this rule, right? Iota d over d phi with d phi is 1 by definition. So now we need to glue among different charts. And well, choose a partition of unity and define theta to be equal sum of alpha chi alpha theta alpha for chi alpha a partition of units. On B. So then, since a partition of unity on B, it's also, so all chi alpha functions, they are automatically S1 invariant. So the whole thing is S1 invariant. And this identity is verified because for each theta alpha, you do get 1. And now you just get the sum of chi alphas, which is 1 because it's a partition of unity. So maybe that one I write. So that's theta. So very well. So such one forms exist. Now let's define a theorem differential of theta, which is a two-form on the total space. And the claim is this theta is basic. Recall, we were discussing those basic forms on principal bundles already. So basic means the following. First of all, this theta is S1 invariant. So this is obvious because theta was S1 invariant. And the theorem differential commutes with all diffeomorphisms. So this is because theta. So the second condition to check is iota v d theta equal to 0. So why is that? Well, let's use, as usual, the Bertin's magic formula. So iota v d, we're replacing it with L of v d iota v. Now LV theta is 0 because of invariance. So what remains is minus d iota v theta. But iota v theta is 1. So this is indeed 0. So what does it mean that it's a basic form? So if I denote the projection by pi, this means there is a unique two form on the base such that pi star of f is d theta. Note that pi star df is equal to d squared theta and is equal to 0. And since pi star is injective, this means df is equal to 0. So we've got, we defined connection 1 forms. So in principle, there are many of them. So, but we showed that they exist. And we see that the theorem differential of a connection 1 form is basic. So it defines a 2 form on the base, and this 2 form is necessarily closed. In fact, it would be one more exercise to show that the cohomology class of f does not depend on the choice of theta. Right? So for kind of different connection, so you can choose different connection 1 forms, and these different connection 1 forms in principle would give rise to different f's, but the cohomology class wouldn't change. But at the moment, for us, maybe we leave it as an exercise. But some of you probably do know it, right? Okay, but let's stop it here. Right. Okay. Very well. So now we're gonna use this machinery to build a local model of our Hamiltonian S1 space in a neighborhood of the level set. So, so recall we have S1 acting on M omega. We have this function mu M to R and x naught mu of M is a regular value. Perhaps just to recall, there is the following picture, right? So there is the level set of x naught. It is embedded into M, and we usually denote this embedding I x naught. And there is a projection pi x naught to the reduced space which is mu minus 1 of x naught divided by S1. And the key formula of the reduction theory was the restriction of the symplectic form here to the level set descends and defines the symplectic form here. Right, so that's the reduction theorem. So that's our context. So I would like to build a simpler local model of M near the level set. The idea is as follows. Let's consider a new manifold, M tilde, and this will be just our level set. Times R. Let me recall that actually this projection, it's exactly a principal S1 bundle, right? So this is an example of the construction that we were discussing before. So I would like to equip this space with a symplectic form. It already has an S1 action, right? So here we already have an S1 action. So this is an S1 space. Now what about the 2 form? So let me take the 2 form to be the restriction of the 2 form of M to the level set. And I would like to add, or maybe more like subtract something from there. Let me denote the coordinate here by y. So this will be the coordinate on R. So I will subtract d of y times theta, where theta would be some connection, one form that I choose on this principal bundle. Connection on v minus 1 of x naught. What can we say about this, this form omega tilde? So simple things we'll perhaps prove, and maybe more involved things we leave as exercises. So what can we say about it? First of all, it's clear that it's closed, right? Right, so it is Ix naught star d omega minus d square y theta, and this is all equal to 0, right? This is 0, this is 0. So it's closed, that's clear. Right. There we go. Now maybe the next thing which is easier, we can compute iota v omega tilde. So v, I denote the fundamental vector field of my S1 action. So what will it be? So it consists of 2 parts, iota v x naught star omega minus d minus iota v d y theta. So let's discuss each of these terms separately. First of all, as experts, what would you say about this first term? May I commute this contraction with the restriction?
Is it a general view, or is this V a fundamental vector field, or is it a general?
V, yeah, the fundamental. This is the fundamental vector field. V. Yeah. Yeah, just the first test question. May I commute it with the restriction? It depends on what? On whether this vector field is tangent, right? So you have a submanifold embedded somewhere. So this V better be tangent, right? The S1 action better be tangent to your submanifold if you want to, but it is, right? So the moment map is S1 invariant. So this means this is iota x naught star iota v omega. Now, what is iota v omega? So, yeah, right. So normally it is something like d mu psi, but now we just have one function. Mu now is just a function mapped to R. So what will be this guy? So it is just like a pairing in R. You take a pairing with your chosen element of R, which you denote by 1. So you have R and R star, which is also R. So what is this? It is D of what? Just of mu, right? So this is d mu. But now what is this? So you take this form d mu, the one form, and you restrict it to the level set of mu. Then what do you get? 0. Yeah, it is plain 0. Right? You take a form dx and you restrict it to the point x equals 0. There is not much left. So this is just 0. Now what about this? So we have minus iota v, and maybe we write it dy theta plus y d theta. So I computed the Duram differential. Now what would it be? Iota v acting on dy. So the S1 action doesn't touch y, so that's 0. Now acting on theta, it gets 1. It will give us 1. Now what will be the sign? Will it be plus dy or minus dy? Plus. You're right. Plus dy, because this guy is odd, this guy is also odd, so when we go through, we get a minus sign. Now what about iota v acting on d theta? That's something that we just computed on the other blackboard. So this is 0, right? Omega tilde has a moment map, and this moment map up to a constant is equal to y. And finally, what about omega tilde being non-degenerate? Perhaps I don't want to do all the details, but let's just informally discuss why it is non-degenerate. So it consists of 2 terms, right? What about this guy? So that's the restriction. That's the restriction of the 2 form to the level set. So how big is the kernel? So this 2 form has a kernel. How big is its kernel? So the 2 form is restricted to the level set. Its kernel is what? We actually already know a little bit, right, of its kernel. So so we have the level set. Right? And so here is the tangent space. That's the S1 action acting on the level set. And so the tangent to the S1 action is in the kernel. Is there any more kernel? We actually know there is no more kernel, because when it descends, when we divide by the S1 action, here it must be symplectic by the reduction theorem, right? So it's not allowed to have more kernel than this. Now in our manifold M tilde, we're adding one more direction, this y direction. So the two form in particular, it has this part, dy theta. Dy theta, that's exactly a pairing between this vector and that vector, right? So it's supposed to kill the kernel. So it's clear that this guy plus that guy is non-degenerate. Now, if you add this guy, we actually don't know whether it's non-degenerate. But this guy is equal to 0 when y is equal to 0, right? So it's non-degenerate when y is equal to 0, and then it's going to be non-degenerate on some open neighborhood. Right? So we actually know that it is non-degenerate on mu minus 1 of x0 times some open neighborhood of 0. But actually, outside that, we don't really know. So when I said that this is a Hamiltonian S1 space, this was actually not true. So there is some open neighborhood of the of mu minus 1 times 0, which is a Hamiltonian S1 space. But since we want to build a local model, we actually don't need much more than that. So I suggest to make a 10 minutes break, or 15, let's say 15 minutes break. And how is it? Probably, again, since next time many people will be away, what do you think? I think my program for today is probably a bit longer than the end of the second hour. So then we're going to eat a little bit of exercises, but we probably want to finish today's program. Is it okay for you? All right. So yeah, let's have a 15 minutes break. All right, so let's continue. Okay, so we decided that on M tilde, so this omega tilde defines as of mu minus 1 of x0 times 0. Right. So now perhaps let me denote by j x0 the embedding of this level set into M tilde, so that the image is the image being the product of the level set and 0. So then note that by definition we have mu minus 1 of x0 embedded in M and embedded in M tilde. So here we have I x0, here we have j x0, and I x0 star omega is equal to j x0 star omega tilde, right? Because when we restrict to the level set, all this part disappears again. So then by the coisotropic embedding theorem. So recall we proved various normal form theorems long ago, the Derbouze theorem, and then Lagrangian embedding, and then I don't think we proved it, but I think we stated it, the quasitropic embedding. So by the quasitropic embedding, so you have this submanifold is sitting inside these two symplectic spaces, and the restriction of omega to this space coincides. So this means there are neighborhoods of these two embeddings which are symplectically diffeomorphic. So so there is a neighborhood V in M tilde and in M, and phi from V omega tilde to U omega a symplectomorphism. Moreover, this symplectomorphism maps restricted to the level set itself. Sorry. Is the identity. And as usual, we didn't prove the equivariant versions of these theorems, but once you have an action of a compact group, as here we have an action of S1, and everything is invariant, under this S1 action, we can also arrange phi to be equivariant under the S1 action. So this is an extra piece. My S1 equivariant coisotropic embedding, and here phi is S1 equivariant. So to summarize, we've got a piece of M tilde, so there is an S1 action, there is omega tilde. So here we said that we can choose mu tilde simply equal to y. So here there is a kind of open neighborhood of this level set, and similarly there is an S1 action on M omega mu. Here there is this open neighborhood, and phi is a symplectomorphism. So basically we've built a local model. There is one question though, whether this phi intertwines mu and y. Whether it intertwines mu and mu tilde. What do you think? So basically we can now identify with this symplectomorphism, we can identify omega and omega tilde. For instance, we pull back everything to here, right? Now, will the moment map mu pull back to the moment map mu tilde? How is it with the uniqueness of moment maps? Right? We fortunately still have an equation here, right? How many solutions does this equation have? What can we put here? Right? If our level set is connected, as we know it is, we can add to y an arbitrary constant. Right? What's the constant that we should add so as the moment maps would match? At the moment, what's the value of the moment map on the embedding of mu minus 1 of x0 to m tilde? What's the value of y on this guy? It's 0, right? What's the value of the moment map mu on mu minus 1 of x0? It is x0, right? So they don't necessarily match. So what should we do here, right? So this was actually perhaps a wrong choice for the moment map. So what should we take here instead? Yeah, exactly, right. So we should shift it by x0 so as it would take a value x0 when y is 0. And now, because the moment maps satisfy the same equation, so their differentials are the same and they match on the level set, they will match everywhere. Right. So now we do have a symplectomorphism which intertwines the two structures. This means that whatever we want to know, at least locally, about this structure, we can study it here. Right? So now phi intertwines all structures, S1 actions, two forms, and moment maps. Well, now what we wanted to do becomes a relatively easy exercise. So, so we choose X within some small neighborhood of X0. And now we know what is the small neighborhood of X0. That's the neighborhood where the normal form is valid, right? Because that's our tool to compute things. And we want to compute mx. Well, by the local normal form, it is the same as the reduced space for m tilde, because we identified locally m and m tilde. Now, what is this? So these are points my in mu minus 1 x0 times r, right? Such that, well, first of all, the moment map x0 plus y should be equal to x. And we should divide it by the S1 action. So this means this is mu minus 1 of x0 times the point x minus x0. And this is divided by the S1 action. And of course, this is the same as mu minus 1 of x0 divided by the S1 action. And by definition, this is m x0. So this is probably even equal. Right? So we see that when this normal form applies, the reduced spaces, they are all the same, right? Because the action is so easy that just the action of the level set and this moment map direction, it doesn't change anything. Right. Now, what about two forms? So we would like to know how the two form here looks like. So I denote by J the embedding of the level set in the case of m tilde. So we want to know what is this Jx star of omega. So I have this mu tilde minus 1 of x embedded by Jx to m tilde, and here there will be pi x to mx. Right. So this is J x star, and so the form here is ix0 star omega. What was it? Minus dy theta minus y d theta. Right? So that's what it is. Now, so the first term it doesn't change, right? So all these level sets we decided we identified all of them, right? So Now we embed it again somewhere, so this term does not depend on any x or any y. So this term just remains the same. Now again, can you help me with these two terms? So what happens with this term, dy theta? So that we already studied once. What happens with the form dy when we restrict it to the level set of y? Right? So this will vanish. Now what about this one? Will it vanish? Not necessarily, but we should put y to be equal to something. To what? If our moment map is x, then y is equal to x minus x0, right? D theta. But now recall that by reductions theorem, so by reductions theorem, this guy is pi x0 star omega x0. And what we discussed by the calculations with S1 bundles, so this guy is pi star f. But you know, this pi x star, pi x, pi x0, since we identified all the level sets, so they are all the same. There is only one pi. Right? This is the projection from the level set to its quotient. So this is actually equal to pi star omega x0. So here x minus x naught minus x minus x naught f. Well, so we would like to read from it the two form on the reduced space. Well, we can read it. Right? Here it is. So the two form on the reduced space is the two form on the reduced space at our chosen level minus this linear function x minus x0 times the curvature two form. So we see that's a great formula. You have, so the reduced spaces are all the same, and the two forms do change, and they change linearly with the level set. So it's a very, very beautiful, very simple outcome. And especially this is a nice geometric thing, which is just a feature of our circle bundle over the reduced space. So, and that's the two form that we started with. So recall that we had three statements in our theorem, and this proves number one, right? All the level sets or all the reduced spaces near a regular value, they are all diffeomorphic. Now, they're not necessarily symplectomorphic because the two forms change. So these symplectic forms are not necessarily symplectomorphic. But now what we can discuss is the volume function. So let's take the volume function, which is an integral over mx of 1 over n minus 1 factorial omega x to the power n minus 1. So why do I have here n minus 1? So the dimension of m is equal to 2n. The dimension of mu minus 1 of x0, a regular level set, is 2n minus 1, right? Because we just take one equation, mu is equal to x0, and that's a submanifold of codimension 1, and then dimension of mx equal to, of course, dimension of mx0. So you subtract, again, 1 because you divide by a free action of S1. So it is 2n minus 2. So that's why here we take the degree n minus 1. So now this is the same as an integral. I now identify all the reduced spaces. I have 1 over n minus 1 factorial. And here, well, I just substitute my formula, omega x0 minus x minus x0 f to the power n minus 1. Well, now it is obvious that this function is a polynomial in x, right? Polynomial in x. And it is also obvious that what's the possible top degree? We don't know whether the corresponding coefficient will be 0 or non-zero, but the maximal degree in x that we can possibly obtain is n minus 1. And that's a proof of 2. So what was right? What was number 3? So number 3 is we want to compute the Duistermaat-Heckman measure, right? So I recall DHM is mu star of L over n factorial. Okay. So I think in the introductory, in those introductory lectures you had before the term started, so there was a little bit of a discussion of fiber integrals, right? Was there? So let's let me write it as a fiber integral. So now I would like to interpret this Duistermaat-Heckman measure again as a volume form. So right, we are alternating a little bit because the thinking of something as a measure and as a volume form. So let me locally think of DHM as a fiber integral, and let me write it in the following way. So it will be fiber integral for the map mu from m to r of 1 over n factorial, and here will be omega to the n. And I'm thinking of it locally, right? I kind of near where our analysis applies. Right? So here I would like to, so I model m by m tilde, and m tilde I recall is mu minus 1 of x0 times r. So I would like to compute this fiber integral in 2 steps. So the first step will be using a map from mu minus 1 x0 to r to mu minus 1 x0 mod s1 cross r. So in other words, I want to integrate over the s1, over the fibers of this s1 action. So this is m x0. So when I do this integration, I will obtain a top degree form on mx0 cross r, right? And now I would like to integrate it over the mx0 directions, right? So I first integrate, so I have a fiber integral, and my fibers are all isomorphic to this principal S1 bundle. So let's first integrate over the fibers of the S1 bundle to go back to get down to the base, and then let's integrate over the base, right? So this is like kind of I do Fubini twice. Okay, so let me. So let me continue the calculation here. So that's my integral over the reduced space, and here I would like to rewrite this integral in the following form. So again, I have an S1 bundle, and I'm integrating an S1 invariant top degree form, right, over those S1 directions. So let me just write a claim, and then you will say whether you agree with it. So the result will be the length of the circle times contraction of the fundamental vector field of this top degree form. Just maybe to make it a bit more clear, so how did it work? If you can imagine how it looks like locally, right? Our top degree form was a product of some, well, maybe let me write it maybe this way, d phi, and then the product of local coordinates on the base. And here there was a function which did not depend on phi, right? Because it was invariant under the action of S1. And then we were integrating it over d phi. So this would mean that we would kill d phi, right? And multiply by the length of the circle. Killing d phi, abstractly speaking, that's contraction with the fundamental vector field. So that's how it locally looks like. So you need to kill d phi, and then you need to multiply by whatever was the length of your circle with respect to your vector field. Traditionally, people choose the length of the circle equal to 2 pi, even though sometimes, I don't know, here you can also choose it to be 1 or whatever you want. But if you choose it to be 2 pi, so then this will be the formula. So that's the integration along the fibers. Now let's look at what this thing is. So let's compute it. Right. So here we are using our local model again. So I would prefer to work with omega tilde. Like when you apply iota of v to omega tilde to the power n, right? This is a derivation, so this means we'll get 2 pi. Now n, which would cancel one of the factors in the factorial, so iota v omega tilde, and here omega tilde to the power n minus 1. Right? So that's what it's going to give. Right? So that's like taking a derivative. So this will give 2 pi 1 minus n minus 1 factorial. So that we know what it is, right? So that's dy. The contraction, so that's the moment map equation. And this guy, we know what it is. It is this iota x0 star omega. Yeah, let me write it this way. Minus dy theta minus y d theta. Right? To the power n minus 1, sorry. Yeah. Now, a simple observation. Since we already have here dy, we no longer need any more dy's. So this guy, we can simply forget. Right? Now, perhaps one more thing. Again, like I use this coordinate y, but perhaps for me it's nicer to write it, replace it with x again. Remember, we know that y is equal to x minus x0. Notice that here in those brackets we have something that we already see. So this guy is a pullback of the two-form omega x. So this was this constant part, and that's exactly the variable part which varies with x. All right. And actually, we were writing it in local coordinates, but now we are living, recall, we now live on mx0 cross r. So actually this pi we should already forget because we already divided by the S1 action. So we already live here. So what do we get? We get 2 pi 1 over n minus 1 factorial fiber integral mx0 cross r to r, and here what? dy, and here omega x to the power n minus 1. Now, what's going to happen when we do the fiber integral? Well, we should fiber integrate over mx0. What should we integrate? We should integrate the form omega x to the power n minus 1, possibly divided by n minus 1 factorial. So that's just a definition of the symplectic volume of the corresponding reduced space mx, because all the reduced spaces are identified with mx0, but there are two forms, so they differ by this linear term. So this is so in other words, what we get is 2 pi times integral over mx 1 over n minus 1 factorial omega x to the power n minus 1. And so this dy or dx, sorry, I decided to replace it with dx, that's what remains, right? So this we don't touch. And this was 3. No, this was 3. So very well, this completes the proof of this theorem. So what we do before the next break, perhaps I just briefly tell you how this theorem looks like for more general case of tori. And then I will formulate one more theorem. And what we're going to do after the break, we're going to discuss this theorem. So this will be the last big theorem in the course, the Duistermaat-Heckman localization. So we're going to discuss it after the break and the relation to this formula. And then, like next time, at least for those who come, we're going to discuss the proof of the Duistermaat-Heckman localization. So that's the plan. So first of all, remark. So how does it work more generally for torus sections? So we proved something for S1, but what would it be? So we have a torus acting on m omega mu, and now the map is into T star. So we take x in mu of m, irregular value. To simplify things, we assume that the action is free, but this can be negotiated. So this, if it's a regular value, it might have some finite stabilizer, but so this we can negotiate. So so then there is an open neighborhood of x, or let's say x0 as before, such that the reduced spaces will be isomorphic in this, or diffeomorphic in this open neighborhood. So the volume function is again is a polynomial in X. Again, one can give an estimate on the degree. And locally, the Duistermaat-Heckman measure is, let me write it down, and then we discuss a little bit what it is. So it's a volume of T times this volume function, times this polynomial function, times the x, the Lebesgue measure. So that's the multidimensional analog of this formula. T star. And here perhaps one interesting extra observation. So you have a torus, right? And if you want to define the volume of your torus, you need to introduce a volume form, right? So we define this volume, say, with respect to the volume form V, and it should be in wedge top of T star T, right, for each point of the torus. Now, if you choose an invariant volume form, this will be, so here is sitting wedge top T star, right? That what you need to make this choice to decide what's the volume of your torus. Now the Lebesgue measure is more or less unique, but up to a multiple, right? If you want to make a choice of a concrete Lebesgue measure, then you need a volume form in wedge top T star of T star, right? And here is sitting, because Lebesgue measure is translation invariant, so you need actually an element of wedge top T star star, which is just T. So you see here you need to make a choice of a top degree form in the wedge product of T star, and here you need to make a choice of a top degree form in the wedge product of T. Now these choices, you should coordinate them such that the volume that you choose here is due to the volume that you choose there. So choose VV prime equal to 1, because there is a natural duality between these lines, and define the volume of T using this volume form, and define the Lebesgue measure using that volume form, and that would give you a unique way to write an answer. That's what we have implicitly done here. So we've chosen the volume form on R, and then the corresponding volume form on S1, such that, remember, we were discussing whether the length of S1 is 2 pi or 1. So we've chosen here the volume form on S1, which was basically d phi, where phi is an angle. So then the integral of d phi is 2 pi. And then, according to that, we obtained the Lebesgue measure, which is dx, and not 2dx and not 1/2 dx. So a similar story would be here. There would be an interplay between these two things. Okay. So let me, as promised, end this hour with the very impressive Duistermaat-Heckman localization theorem. Right. So we formulate it for torus actions, and then we again mainly discuss it for S1 actions, but a little bit for torus actions as well, and we prove it for torus actions, I think. So again, we start with a compact connected Hamiltonian T-space. And we assume, this is to simplify our considerations. We assume that the fixed point set is a finite set. One can formulate it in a general case, but this would require more machinery, and maybe that's not what we want at the moment. So then there is the following formula. For the integral with respect to the Liouville measure of the exponential function, exponential of mu psi, and we'll discuss what psi is in a second. So psi, in any event, psi is an element of T, but there will be some further conditions on it. And here there will be 2 pi to the power n, where n is before is a half of the dimension of the manifold, and then sum over points in MT, and here there will be exponential mu of m psi, and here will be the product over J and J of m psi, where we know that for fixed points, the tangent space is a direct sum of copies of C, where on C there is an action. So C and J of m. So these are weights of T. T action. So for each fixed point, there is a set of T weights. So so these guys are integral elements of T star, and so we take a pairing. We take a pairing with psi. So as I said, psi is an element of T, and the formula is true whenever it makes sense, meaning that we want all these denominators, right? So on the right-hand, the left-hand side is very nicely defined for all psi. The right-hand side is a priori not so nicely defined because there are all these denominators which are products of linear functions. So then we require that all these linear functions, they're well defined, so they should be non-zero. In particular, this is certainly true if T psi, so the closure of the one parameter group generated by psi, if it is the full torus. So then it's impossible for those products to be zero, because then the T representation, one of the T representations would have been trivial, and this is not supposed to be the case if our point is an isolated fixed point. So this formula is always true when it is well defined. So that's very, very, very interesting formula. And I suggest let's again have let's have a 10 minutes break, and after that we continue. But we're not going to prove this theorem today. But we're going to discuss examples, and we're going to see how it works. And also we make a link with the previous formula that we obtained, because you see, before we were having some push forward of the Liouville measure, which was a Duistermaat-Heckman measure, and we figured out that it's related to the volume function. Now the question is, can you combine the two tools? Can you extract for instance, some information about volumes from the fixed point from the Duistermaat-Heckman formula? And that's what we're going to do at the next hour. All right. So let's have.